All right, I guess we will start. So we are here today to demonstrate some binary exploitation. I am Marit, and this is 0xBadCafe1 on Twitter. I can take this.
Yeah, perfect.
Will you introduce yourself?
Oh yeah, that's me first actually. Yeah. So my name is Christian. I currently work as a security engineer in Google's threat analysis group, where we track like serious threats against our products. Yeah, and I've previously done work as a vulnerability researcher, and I've done malware analysis, reverse engineering, and so on. So yeah, and I'm also a huge hummus enthusiast. So I've said this at other conferences, but I still haven't gotten any like good recipe tips. So please hit me up after the talk. Also play a lot of CTFs, and if you're not familiar, it's a form of hacking competition, and I have a play with a Norwegian team called Bootplug.
Yeah, all right. So my name is Marit, and I work at a consultancy company called Sopra Steria. And there I have two roles. So I work a little bit as a business developer, which is more or less a subject matter expert, and my domain is secure development. In addition, I just cannot stop doing software development, so I work as a software engineer as well. I'm also part of Bootplug. I'm a board member of a security group called Oslo CTF for beginners to give them a good start in the security community. And I'm also part of the group for non-binary people and female women, which is called Pound and Puff Girls. So can we just switch? So I have this one. Thank you. All right, so our main thing today is to talk about a bug in sudo. And yes, when I say sudo, I mean sudo like when we write sudo apt install, or like I like to say to Christian, sudo get me a sandwich. And so that's the main goal today. But to make sure that most of you can follow that bug, we want to briefly introduce binary exploitation, then go through the stack and the heap. And then in the end, we will go through a couple of preventions and protections. So how many here have heard about binary exploitation? Yeah, that's a lot of hands. Cool. And how many of you have written an exploit? Wow, that's actually a few hands. Yeah, cool.
Nice.
So Christian obviously have written an exploit because he wrote the exploit for sudo, which is the one we are going to demonstrate today. Oh, okay. So when I'm going to explain what binary exploitation is, I want to do it by explaining the word pwn, P-W-N. Pwn is what we call binary exploitation in hacking competitions. And according to Oxford Dictionary, it means to utterly defeat or completely get the better of something. In our case, that something is a binary, right? An executable file. So it is unavoidable to mention memory safety when we talk about binary exploitation. And we have a couple of memory safe languages, such as Java, C#, or Rust. And then we have some memory unsafe languages, such as C and C++. And to illustrate that, I'm going to show you some code snippets. We low code, so we try to put a lot of code in our slides. And we start by looking at this Python script. What it does is that it outputs GIF username to standard out, and whatever is written in standard in is stored in the variable username. And then we print hello username. We see the example on the bottom. I write my username Maritio, and it says hello Maritio. But how does this look in the memory unsafe language C? It can look like this. We allocate 24 bytes on the heap, and then when we read the username from standard in, we allow writing 24 bytes into the username variable. And then when we're finished using it, we free the username from the heap. Point here is that we need to handle memory. We need to have control of the memory and how to allocate memory in a proper way. If we don't do it properly, we might introduce vulnerabilities. And that's exactly where binary exploitation comes into the picture, when we don't write the memory properly. There are a couple of vulnerability types that are common. Many of you might have heard about stack overflow, which is also called buffer overflow. Other common are heap overflow and then use after free. These are just some examples. And we really wanted to show you some code snippets and explain those to you as well, but we simply don't have time for it today. But then, Christian, you know, while I'm in development projects, at some point we usually start talking about binary exploitation. And one thing that often comes up is that, okay, we're talking about buffer overflows, and one person almost always says, but that's so old. Is it even relevant anymore? It probably isn't. Do you agree?
Yeah, that's something I hear a lot as well, and I don't really agree, because if you look at some of these like big companies, like for example Microsoft, they had some statistics where they said like 70% of the vulnerabilities that they patch in their products with like a high criticality, like very severe vulnerabilities, are memory safety issues, like use after freeze, buffer overflows, and so on. And the Chrome team, the Google Chrome team, had like similar statistics where 70% or around 70% of the bugs that they patch in Chrome or vulnerabilities they patch in Chrome are actually memory safety issues. With, for example, use after free being one of the most common ones. And these are examples of like companies and products that are very mature when it comes to security. Like they have a lot of defenses mechanisms in place and so on. But then on the other hand, you have products that, for some reason, will just disable all of these defenses that we have available today. For example, from the compiler or whatever. So yeah, it's still a very prevalent issue today, even though this has been a problem for many years.
Yeah, that's super interesting. Both Microsoft and Google have like the most of the vulnerabilities are memory safety issues. So this is highly relevant. It's not all news at all. Oh, I forgot to mention one thing. If you see on the top of the slides, we have this Google link. And if you want to ask questions, you can ask them there. And then we can bring them up afterwards. We get them on the screen. So feel free to ask questions. You can do it anonymously as well. Yeah, so let's jump into Stack Overflow. One thing that I want to say that was part of the agenda slide is that we want to explain Stack Overflow before explaining Heap Overflow, because we think it's a good segue. It's easier to learn about the heap when you know about the stack. And the bug in sudo is a heap overflow. So that's the thing that you will want to understand the most. So the stack. Let's start with that. The stack is a memory region for temporary storage of data. And that's all I'm going to say about the stack. Then we just look at the code. So let's take a look at this code snippet, which is very similar to the one in the beginning. But it has this struct called user with 3 members. And when we run the program, we initialize the user struct called hacker by nulling out the name and setting the name, the age and is hacker. then when we read the username, we allow reading 50 bytes from standard in. And some of you might notice a vulnerability here, but hold your horses. You are going to get the opportunity to tell us what the vulnerability is, but not just yet. But Christian, we just moved to Switzerland, right?
Yeah.
And I heard that there is something there that is really...
Yeah, they're known for their cheese, right? So we have some cheese to hand out?
No.
No, okay.
We have some chocolate, because we're really known for chocolate, right?
Yeah.
Did we even... yeah, we have them there. So we have 2 small bags with chocolate. And we were thinking that we have 2 questions, 2 vulnerabilities that we want you guys to point out, you people to point out. And there is one here, which you will be able to answer afterwards. But first, let's look at how this program's stack looks like. The first thing that happens when the program runs is that the function prologue, this thing called function prologue, you don't need to understand that, sets up the stack frame by setting up the return address, the saved base pointer, and then some space for the local variables. In our case, the local variables are the members of the struct. And that is because each function in each program has its own stack frame. In our program, we only have one function, which is the main function. So we only have this one stack frame. So if we look at the stack frame, we see that we have 16 bytes for the name, 4 bytes for the age, and then 4 for isHacker. A Boolean is 1 byte, but due to stack alignment, we need to pad to 4. Saved base pointer represents the beginning of the stack, and it's used to access the local variables. But then the most interesting thing here is the return address. Because when a function finishes, the return address is the address in the memory that the program will run the next code from when the function has finished. And we'll come to why that's very useful and interesting. Oh, it's now the time for... No, there's one more thing I want to say. And it's that usually when I learn things, I tend to think okay, I understand this stack frame thing now. It's for every function, and okay, it's how the stack frame looks, but how does it really work in the big picture? So I decided to draw this illustration because each process has their own stack. So this program has its own stack, another program has another one. So if 2 processes tries to access the same memory address, they will access different data. If the main function would call another function, we would have a new stack frame underneath, because this is like a LIFO structure, last in, first out. And if that function again would call another function, we would have another stack frame on the stack. And all the things that you see at the top of the main stack frame is just like standard libc stuff that's not so important for us to think about. So back to the Stack Overflow. Now is the time to raise your hands. Who can see the vulnerability? I saw the first hand there.
You're reading in more bytes than you have on the stack, so you can overwrite the return.
Yeah, exactly.
Yeah, chocolate for you.
So what she said is that we allow reading more bytes than we have space for in the name. So when we store whatever is written in standard in, we overwrite on the stack up to the return address, and we can overwrite the return address. So let's take a look at this illustration, in which I've written an sort of exploit. And for every variable, I've decided to use like A, B, C, D. And I write 16 A's to represent the name, then 4 B's to overwrite the age, 4 C's to overwrite is hacker, but then we have this really strange thingy in the middle. Like it's just blank, but we have 8 D's. And that's because of stack alignment. I mentioned that previously, and the stack has to align with 16 bytes. And then in our case, that will be to 32. And then we add just 8 Ds. We also don't care about what is on the saved base pointer, but we definitely care what is written on the return address, because there we can put some address that we control and run our own code. To run this example, we compiled the code with a flag that turns off a security mechanism. It turns off something called a stack cookie or a canary, and it would go between the saved base pointer and the local variables to make sure that we cannot overwrite in this way. However, just like Christian mentioned previously, a lot of people turn that off. So it's still valid, right? It's still a valid example. So I send all of this in to the program, and we see that the program segfaults. And it says like, codebabe in question mark. That really means that it tried to run the code in codebabe at the memory address at codebabe, and it didn't work. But that means that we have control of the code and can run whatever code we want. Okay, I think that was the everything for the stack. Are there any questions about the stack?
There's one.
There's one here.
Should we answer that now or do it later?
Oh, I don't know the answer of that. Let's just put it on.
See if this works.
I hope that you have some thoughts about that.
Yeah, maybe. So the question was, did anyone consider making a stack growing in the opposite direction to mitigate some attacks? And I guess the growth direction of the stack doesn't really matter, does it? Even though it grows downwards, we're still writing up because the stack grows from high to low memory. But when we read and write from buffers, we go from low memory to high memory. So I guess they would have to completely move. I mean, they would have to like switch the order completely of whatever's on the stack, like the saved base pointer and the return address and so on. I guess they could do it, but you would still have the problem of like overriding adjacent variables and so on. So it's still an issue. So I think the stack canary is the best solution, maybe. But
yeah. Good question. Oh,
we can do this later, maybe.
Yeah.
Yep. Okay.
Okay. Hide.
Yep.
Okay. Awesome. So now we learned a little bit about the stack, and we can see that if we input more input than what is it's supposed to be, then we can manipulate the program to do something else. And let's take a look at the heap. So the heap is very similar to the stack, except for that the stack has static memory allocation, which means that the space is determined at compile time, while the heap uses dynamic memory allocation. So we get the space runtime. There are a couple of APIs, just for reference, like when you use the heap. For instance, in our code snippets, we use malloc and free. while in C++ you can use delete and new. And there are also a lot of memory allocators. The memory allocator we use in our snippets is glibcmalloc. Others are like scudo, partitionalloc, jmalloc. And the thing with all of these is that they have this, what did I call it? Like trade-off, yeah, between performance and security. So some allocators, they enable security mechanisms, others disable the same. And it depends on your system, which one you should use. And then back to the code snippets. For this one, we allocate 32 bytes on the heap for a username, or the username, and then 64 bytes on the heap for a command. And then we copy the string date into the command variable. When we read, the only difference here is that when we output the username, we also run system with the date command. And we hard-coded the date command, right? So it will always be the date command, right? The same thing here. There is a vulnerability. And you will get the opportunity to let us know what the vulnerability is and get some chocolate. But first, we're going to look at how the heap for this program looks like. This is our best effort of illustrating the heap. It's not that easy. And the heap for this program simply has 2 chunks. And what we call each allocated space for a variable is a chunk. So we have a chunk for the username, and then we have a chunk for the command. They are right next to each other, and when the program runs, whenever the malloc function is called again, it will find the next free memory space and then store the variable there. So for the intended way of running this program, we could insert foobar as the username, and then foobar would be what's stored in the username chunk. And then, of course, the date is always date in the command chunk, right? So then when we run it, it says like if username, foobar, hello foobar, the time is, and then the date. And now, are there anyone who wants to say what the vulnerability is?
Oh, I think you were the fastest.
So if you use, I don't know, if you overflow the username, is there a possibility that you might actually put another name in the command function?
Yeah?
Okay.
Will you repeat?
Yeah, so I think what you said was, like, if we put in more data than this username buffer can hold, we will actually end up overwriting the command. And we can put something else there instead.
Yeah, definitely. Do you have any thoughts on what would be fun to overwrite with?
No, I don't know C.
Oh, all right. But I have a very funny, I didn't do it. Christian came with a very funny idea of using cow say. So we just insert a lot of A's until right before the date chunk, and then we overwrite with a command we wanted to run. And one thing that is really important to note here is that we did not turn off any security mechanisms. So this is just compiled totally correctly, and yeah. And then when we write this input instead of the username, we get this output, which is instead of the date, cow say, in which we can run any command we want.
We have to remember to change this for JavaZone.
Yeah.
It doesn't say hello.
All right. So that was introduction for the stack in the heap. And I just have to say this, that it can be really hard to understand. And like, if you don't get it, it might take a couple of times to understand how the stack and the heap work. So please do not feel down or feel bad about yourself if it's hard to understand. It really might be a little difficult. Are there any questions about... we have some more questions now, actually.
Yeah, want to do them now, or
we can do them later. Then we know we can...
Yeah. We'll do them later.
Yeah.
Yep. Thank you.
So then over to the real-world example.
Yes. So let's dive right in. Can we change?
Yeah.
Try not to fall behind the stage. Yeah. All right. So this real-world example that we chose is a bug in sudo. And just to make it clear, this is not found by us or anything. It's found by a company called Qualys. They do really cool research, so if you like this kind of stuff, you should really check them out. They publish a bunch of really cool papers about attacks on usually like really like common software, like sudo is found everywhere, right? On your servers and stuff like that, and your desktops. So yeah, really good work by them. And this is a heap overflow in sudo edit. And sudo edit is just a symlink to sudo that you use, that sudo kind of picks up that it's being launched as sudo edit, and it's used to edit files instead. And this bug allows privilege escalation to root. So if you're not familiar with Linux, root is basically admin. I mean, you can do anything once you're root. And just as a fun fact here, so me and another guy, when Qualys published the details about the sudo bug, they only published like, this is the vulnerability, this is how we exploited the vulnerability, but they didn't publish any code to actually exploit the vulnerability, to limit the damage that this can do. So they didn't want anyone to copy paste code and go ahead and exploit servers. So, but me and another Danish guy, we were playing around with this bug because it was interesting, and we wanted to see if we could recreate the research. And after a couple of days, we were able to create a stable exploit for this one version of sudo, and could probably take it further for other versions as well. It just goes to show that like we were just playing around and got it working in 2 days. So someone with more skill and motivation would be able to do it quicker, probably. So when like reports like this are published, it's probably a good idea to patch quickly, or else people will, jump on it and try to abuse it very quickly. All right, so let's dive straight into the code. This is the vulnerable piece of code in sudo. And there are some like requirements for getting to this vulnerable piece of code, but I'm not gonna get into the details. You can read the full report if you're interested. But we're gonna go through this step by step, so don't worry if you don't understand it like right away. So the interesting thing here at the start, we're just gonna start in the for loop. There are these two variables that are being assigned to or from, and it's to and AV. So to here, you see it's assigned from something called user args. And this is a heap buffer. And Marit said this is a heap overflow. So this is the first clue. And user args, it's allocated beforehand, and it's supposed to be able to hold every single command line argument that's passed to sudo. And you can see AV here comes from new argv plus 1. So if you're not familiar with C, argv is basically just a list of all the command line arguments that are passed to the program. And plus 1 is to skip the first entry, which is just the name of the program. So we're only interested in whatever flags or names of files or whatever is passed to sudo. And then the condition here is just checking we still have more entries in this argument vector. And then we're just looping through everyone. So every single command line argument is looped through. And we're constantly assigning to this user args buffer. So then comes this while loop. So if you're not familiar with C, strings in C are just a sequence of characters that's like ended with a null terminator. So it's just a zero byte. And there's no, like in other languages, there's no size attached to this data. So when you're like going through a string to see how long it is, you have to kind of count until you reach a 0, and then you're, oh, okay, it was this long. which might sound insane if you've never programmed in C before, but yeah, that's how it is. So what this while loop is checking is that it's just checking, are we at a 0, which means is this the end of the string? And as long as that's not true, we're looping. And then there's this complicated if test. We're just going to skip that for now, and you see this assignment. So this as well is maybe a bit confusing syntax, but what it's doing on the right-hand side is that we're dereferencing from, that's the star, we're grabbing one character from this buffer, or this pointer, and then we're incrementing it. And then on the other hand, we're storing that character into 2, and then incrementing it. So this loop is just doing string copy, if you're familiar with C. If we ignore the if test, so it's just copying characters as long as we're not at the end of the string. But then comes the interesting part, is this if test. So it's checking, are we currently at a backslash? You know, because this is handling escape characters somehow. And then it's checking, is the next character not a space character? So which means a space character, at least from ISSpace's like point of view, it's a new line, a space, a tab, whatever. And then if this is not a space character, like if it's ABC or whatever, it will go into this if block and increment from, which means we skip the backslash. So the bug here is, if we imagine that we're at the end of the string, and we have a backslash all the way at the end, this first check will pass, like from 0 is a backslash, and then we check the next character. And if you remember what I said, like every C string is terminated by a 0. So it will check, is this 0 a space character? And it's not considered a space. So we go into the if block, and we increment the pointer, and now we're actually looking at the 0. And then when the if block is done, we copy the 0 and then increment past the end of the buffer. So at this point, we're outside of the memory that we control. We're suddenly out in, you know, undefined behavior land, as we call it in C. And we keep storing, like if there's some, you know, if there aren't a bunch of zeros there, we keep copying whatever garbage is stored after into this user args buffer, which is only, which can only hold, you know, or it's only designed to hold the number of characters in the command line arguments. But suddenly we can copy more. Yeah, there's the clicker. So this is how it could look like in memory. Like if we imagine that we have, like on your left-hand side, we have these two strings, hey, with a backslash at the end, and then bye. And for some reason, they're stored after each other in memory. And if we look at like the result of this operation on your right-hand side, you'll see that we copy first hey, we get to the backslash, and then we just skip it. We copy the 0, and suddenly we're copying memory from this other string that was, for some reason, next to our buffer. So in the end, we have hey, null terminator, and then bye, and a null terminator. So suddenly, we like in the pseudo case, we might have, you know, allocated room for, I don't know, 1, 2, 3, 4 characters maybe with the null terminator. But suddenly we have this other string in there as well. So we've copied way too much data here. Yeah, so let's just kind of summarize the bug. Here's the vulnerable piece of code again. So what we're doing is we're copying data from AV, which is the command line arguments, right? And we're overflowing, or potentially overflowing, this user args buffer. And user args is allocated on the heap. The memory, you know, the size has been determined up front, and sudo has allocated only enough space to hold the characters in the command line arguments. And then another fun fact here is that AV is actually allocated on the stack. So the argument vector, when you start a C program, the Linux kernel will just copy all the command line arguments onto the stack for you. So this memory is actually coming from the stack. Yeah. So let's think about this. So I said earlier that if there aren't any like 0 bytes after this buffer, we will copy whatever is stored there. So our question is then, what's stored after the argument vector, like all the command line arguments? And it turns out that the Linux kernel will first copy all the command line arguments, and then it will copy all the environment variables. and they will be right next to each other in memory, which is very convenient for us because the environment variables can be controlled, which you might know if you've ever used the env command or whatever. So at the bottom here, you can see an example of how it could look like if you have a program called test with no command line arguments and 2 environment variables. This is the layout in memory. You would have the name of the program. That's the first argument vector entry. And then you have all the different environment variables that are just stored right after each other in memory. So also when we talk about exploitation, we often want to know what we control and if there are any limitations, because the more control we have, the easier it is to write an exploit. So in this case, like, are there any limitations? Like, what can we store in the environment variable or variables? And it turns out we can store pretty much anything. It doesn't have to be a string. The Linux kernel doesn't care if you put a PDF in your environment variables. You can put anything there. So that's fully controlled by us by using the execv system call on Linux. That's what you use to start new processes. So that's great from an exploitation point of view. Yeah, so just to kind of reiterate here, we control the overflow size. So like we can overflow this heap buffer, and we also control the contents because it's being copied from the stack or from the environment variables, which we can fully control. And so one thing that's going to be clear later is that it's important for us to be able to write null bytes. And if you remember, like when the code hits a backslash and the next character is a null, it will copy the null and skip the backslash. So by sending in a bunch of just backslashes as environment variables, the sudo will just keep copying 0 bytes and then skip to the next backslash, and this will also be skipped, and then you get the next null byte and so on. So this is something that's actually required for the exploit, and you'll see later how it looks like. Yeah. So the question is then, like, what do we target with this? Okay, we can overflow some data on the heap, but where does it go? I mean, how do we know what's our goal here? So what Qualys did that was really cool, and we actually, when me and my Danish friend were trying to re-implement this attack, is doing sort of fuzzing, where you kind of throw random stuff at sudo, and you see like where does it crash. So by varying the command line argument length, the different environment variables, and so on, the behavior of sudo will change slightly, and you try to trigger this bug or this vulnerable piece of code. And by doing this, like, they were collecting backtraces, which is just with GDB, the debugger. And with the backtrace, you can see, okay, it crashed on this line, and it came from this piece of code or this function. And one very interesting function crash that they found, we were actually able to find as well after running our fuzzer for way too many hours, was this crash in a function called NSS load library. And I have no idea what this function does or why it's there, but it's a part of the standard library, I think. And why this function is interesting from an attacker's point of view is because this is loading a library. And if you load a library that's attacker controlled, you can actually get code execution at load time. It doesn't even have to use your library for anything. And the reason for that is, like you see at the bottom, like the last line in this piece of code, is it calls DL open, which what is it short for? Dynamic library open or something. And if your library that's being opened contains a constructor, this will run at load time. And this is not your, like, if you're used to writing C++, it's not a C++ constructor, but it's a special hint you can give to the compiler to say that this function should run at load time. And that's used by, I think it's used a lot by C++, for example, to do initialization early on when you load the library, and then you can use functionality later on. Yeah. So what we want to do, like, one thing I forgot to mention was that, like, when Qualys found these crashes, and when we found the crashes as well after, trying to fuzz sudo and trying different lengths and stuff, was that this function would crash because I think this library pointer, you can see that it's dereferencing a library pointer in the second if test. And this pointer was just garbage. It contained a bunch of, A's or something. And this will crash because it's not a valid memory address. Which means that we fully control the contents of this service user struct that's passed as a parameter to this function. And if we kind of go through the code, I've kind of shortened it down a bit so it's easier to read. So in the first if test here, we check, is this library pointer null? So we now know that, okay, if we somehow can set this pointer to null, the function will actually initialize it for us, which is very nice. It does all the work for us. And then it gets to this next if test. It checks if the library's lib handle is also null. And this will be true if the first if block is true. And in this case, it will construct a shared library name using this horrible chain of STP copy calls. And the library name will end up being libnss underscore, and then whatever is inside of this service user struct, .so, and then there's a revision at the end, which is .2 for some reason. I'm not sure why. If you know, please let me know. And then at the end, it will open this library. So if we can set this library pointer to null, and then also control the name inside of this service user struct, we can make the code open any library that we control, and thus get code execution. Yeah, so just for completeness, this is how the service user struct looks like. We don't really care about anything except for the library. We need that to be null, so we need to know like where in memory from the start of the struct this is located. And then we have the name at the end. So again, if you're not familiar with C, the reason why it says char name and then 0 is because this is a flexible array member. And it's, in my opinion, a terrible language construct, but whatever. Basically, it's used so you can have a flexible size of the name. So when you allocate the struct, you allocate the size of the struct plus whatever is the name length. And then you have that much space for the name at the end. Yeah, so this is our goal, right? We have this user args buffer, which is stored on the heap, and we're copying, a bunch of garbage from the environment variables. And what we want to do is we want to set this. We want to set the library pointer to null, and the name to. In this case, we've chosen x/x. So the library name will end up being libnss underscore x/x.so.2. So it lives inside of this folder. And the rest we just set the whole service user struct to null. So we just have to overflow until we reach this service user struct, and then we can control everything. Yeah, so this is how our shared library will look like. It's a very, very simple piece of code. The only thing we're doing is we're setting the user ID and GID to 0. And this is root's user ID. So this basically gives us root privileges. And then we start a shell with execve. That's how we launch processes on Linux. And then there's this interesting part at the top there. We have this attribute constructor. And this is like a special compiler magic thingy you can specify, and the compiler will put this function into a special table that will be loaded, or it will be run at load time. So this is how we create our constructor. Oops. Yeah, demo.
All right. So now we'll see how this is how we run the exploit, basically, right?
Yep. Wait, I actually have this running already.
Maybe a little bigger.
Yeah, hang on. Just gonna. Oop. Okay. It's very easy to see. Yep. All right. So so we have this Docker container that we're using to run this, and just so we kind of know that the result will be the same every time. Because sometimes if you upgrade sudo, there will be slight differences, or the standard C library breaks your exploit. And actually, like I mentioned earlier, like me and my Danish friend, we only made an exploit for a very specific version of sudo. So we cheated a bit, and this is not actually our exploit. This is someone else's. Captain Gibbon on GitHub. So all credit for this exploit goes to them. But most of you can find a lot of different pseudo exploits on GitHub, and they will vary a little bit in like their technique. So yeah, if you're interested, there's a bunch of them on GitHub. So let's kind of look very quickly through the exploit before we run it. Sorry, I'm gonna. Yep. All right, is that readable? Yeah, hope so. So if you start at the end here, this is where we kind of launch our exploit. We're calling execv, and we're starting sudo edit. So we're launching this program with argv and envp, which is our command line arguments and our environment variables. So these are our like crafted values that we control. And then we have this huge weird array here. This is the environment variables. So at the start here, we have it's a buffer called Overflow. And this is here for, it's a technique in exploitation that we call heap feng shui, where you kind of want to control how the heap looks like. And so you have to do some weird stuff, and that influences like how things are placed on the heap. So like Marit mentioned in the heap illustration, like this heap allocator will pick like the first chunk on the heap that's of the correct size. So by allocating and freeing and so on, you can kind of control how the heap layout looks like.
And that's what the fuzzing is for, right?
Yeah, that was what the fuzzing was for. So instead of like understanding everything, we just fuzz until we find a cool heap layout that we like. Yeah, let the computer do the work. So yeah, so this overflow is just here to kind of make sure that when we're overflowing, we're copying data all the way into this service user struct. And then you see there's a bunch of stuff here. There's some these backslashes. These will copy null bytes. So we keep copying null bytes, and then there's some x's in there. I think that's to fill one of the fields. And then there's more zeros. And then at the end here, you see x/x. And this will be the library name. So all of this stuff will be copied onto the heap and will end up trashing this service user struct. We also have some more. You see these weird thingies here. So these are what's called LC variables, or yeah, I think that's what they're called. And these are used on your system to specify, for example, what's the phone number format and stuff like that. And the reason why this exploit is using it, here you can see measurement unit, like depending on your country or your region, these might change, right? But in this exploit, these are being abused also to do heap feng shui, because these LC variables will be picked up by the standard library when the program is loaded. So very early on in the load process, these will be picked up and stored on the heap. So by throwing this into the environment variables, this will be picked up by the C library, and then it influences the layout of the heap. So these LC variables is also something that when we were doing the fuzzing, we were changing the sizes of these to see how it influenced the heap layout. And then at the start here, this is the command line arguments. So we have sudo edit, and then we have this s-s flag, and this is actually needed for the exploit. But I can't remember why. It's been a while since I looked at this, but it's explained in there in Qualis's explanation or paper. And then we have this buffer, and you can see there's a bunch of random garbage, and then at the end we put a backslash. And this is what kind of kicks off the whole exploit. So when sudo actually reaches this backslash here, it will start reading into these environment variables. And then it will just keep copying until it reaches the end there. Yeah, so let's see how it looks like.
Let's go to the most exciting part.
Yeah, I guess this is the
least exciting.
Yeah, so we just run this binary. So we compile some code from GitHub, and then we run it. Oh wait, I can also show you.
Yeah, do that first.
Yeah, we also have this library here, libnss _x, and there's this library inside.
Also, maybe show that we do not have privileges just yet.
Yeah. So
That's a really, really important part. We didn't really mention, like, why is it so important, or why is it such a cool kind of bug, since it's pseudo, and it's so cool because pseudo gives us privileges, right? So if we get to exploit pseudo, we get higher privileges.
yeah, so the whole point of pseudo is to give someone higher privileges.
Yeah.
So this is a perfect example of a program that, if you find a bug here, you have, I mean, it gives you free root access. So yeah, let's run the exploit. And it's not very interesting, but suddenly we're root. So just by running this weird binary, we're fully hijacked the control flow pseudo and tricked it into loading a library, and suddenly you're root.
Woo.
So, yeah, woo. It's not very exciting to look at, but behind the scenes, there's all of this weird stuff happening, right? You know, the heap is being feng shuied or whatever, if that's a verb, and then then you fully control whatever's stored there.
But I mean, the feeling of managing to escalate privileges like that must be pretty cool, right?
Yeah, it's pretty fun. So that's why, I mean, people like me keep doing it, and people like us. I mean, it's because it's fun, right? You get that thrill of, messing with this program. Yeah. All right. So quickly at the end here, we're going to go through some protection and prevention tips.
If we do it quickly, we can talk about some of these questions.
I was actually going to ask, how many C or C++ developers, or assembly for that matter, are there in the room? There's 1, 2. Okay.
There's some.
There are some. Okay. Yeah. So first of all, I have to explain why there's a picture of me here. It's not because I like looking at myself, but we wanted to make this analogy because here you can see me. If you're not familiar with Oslo, this is outside of the ER in Oslo because I had a teeny tiny skateboarding accident. And as you can see, I look kind of pleased here because I guess I didn't die, so I was pretty happy. I was wearing my helmet, as you can see on my side there. But the thing was, I didn't wear any other protective gear, and that's why I have all of these bandages everywhere else. It was kind of painful, and yeah.
The irony is that he was saying that I'll bring my protective gear, I'll put it in my backpack, and if I'm going to do something stupid, I'll put it on.
Yeah.
He did something stupid, and he did not put it on. And that just makes the analogy perfect, right?
Yeah, so I thought that was a good analogy because we have all of these different toolings and compiler mitigations and so on that you basically get for basically free. I mean, there's some performance overhead, of course, for most of these security features. But there are a ton of security features that you can turn on in your products that will actually kill off certain types of bugs and vulnerabilities. For example, one example is stack cookies, and we'll talk more about it because I saw there was a question about it. Yeah, and there's all of these other mitigations that make it harder for attackers. And in some cases, some of these can require an attacker to have several vulnerabilities, and that kind of ups the bar, right? So if they're only able to find an overflow, usually that's not enough to exploit a system today. You also need something we call an information leak. In addition, that gives you that reveals some secret state of the program, basically. So yeah. So one thing you could do, I guess it's not the most popular opinion maybe, but it's using memory-safe languages where you can. I know it's not always possible, but we see more and more products that are not rewriting whole C, C++ projects in like Rust or Go or whatever, but they're taking small parts of it. That's especially those parts that are handling untrusted data or parsing some data structures, and they're rewriting those parts in Rust, for example. And that makes it, makes that part of the code. You basically eliminate binary exploitation like problems from this part of the code by doing that. And of course, I mean, there's no like perfect programming language, but at least you don't have these very serious memory issues. Yeah, I think I'm going to skip the rest so we have time for questions.
Questions? Yeah, sure. Yeah.
It's not that interesting.
Can we start with this question here?
Yeah.
I'm just going to read it again.
Oh, yeah, this is a good question, actually.
Okay, present, right? Okay.
Yep.
So the question is, I must be missing something. If all it needs to break is a backslash at the end of the command, how has this not been detected before? Anyone who accidentally ends their command with a backslash would cause an error.
Yeah.
But no, I'm going to do this first.
Yeah.
So at one point, I focus on secure development, right? But really, do all of you actually do like static code analysis or fuzzing or do this on all your programs? They probably didn't, since both the Danish guys and Christian here and Qualis, they did fuzz and then they found it. So that's one of the things, but you can answer the rest.
Yeah, so for in this case in sudo, it's actually reaching this vulnerable piece of code isn't that trivial. So that's why it wasn't found before. Because you need to launch sudo edit and you need to enable this one flag, and that causes some weird, I don't know, parsing of the escape characters or something like that. So it's not, I guess it's not the most obvious bug, but I guess it could have been caught with fuzzing if they've tried different variations of the flags and so on.
And also we saw the heap feng shui, right? A lot of these things needed to be in place to make this work. So
yeah.
I guess it's not that easy.
Yeah. I can do this one very quickly. Isn't sudo password protected? Yeah, it's supposed to be, but this code actually, or this vulnerable piece of code is actually running before the password check. So I think for this, you don't even have to be in the sudoers file, which I think is the case for this Docker image. We just have a random user on the system, and sudo is actually exploited before it can do any checks on the user at all.
That was a good question.
Yeah, that's a very good question. We can do this one, maybe.
Yeah.
I feel as though there's a parallel here to the 737 Max crashes.
Yeah. Did you hear?
Yeah, but I'm not sure what that is. Sorry.
Me
With the
neither.
plane?
You turn off the system that makes the thing crash. You turn off a lot of other systems that also makes the thing easy to fly. So if you turn off the thing that stops the plane from crashing, you're not going to be able to fly the plane properly. Yeah.
Yeah.
Order of concerns.
Yeah. No, that's a good one.
All right, let's just move on. I'm not sure I can repeat that in a good way.
Yeah, let's look at this one. So yeah, you said that binary exploits are still relevant in the modern era, but you're using a language, C, that is very old. That's true, it's very old. Are these attacks really relevant today if you're using modern languages, or only if you're using old languages that let you do things like reading 50 bytes into a 13-byte array? Yeah, so I guess, yes, that's true. It's only relevant if you're using C and C++. But if you look at like projects, or if you're using like, what's it called, like foreign functions interface, or you're using native libraries behind the scenes. Like there was this one case with Python, I think. It was just passing some untrusted data into an unsafe C function. So behind the scenes, like you're looking at Python, this fancy new language that doesn't have memory safety issues, but Python is written in C. So if they parse your data in a bad way, it can lead to memory safety issues. But yeah, I mean, it's mostly these products that are being affected, or if they're using C behind the scenes. Yeah.
I guess we have time for one more question. So now we have to choose carefully.
Ooh. This one maybe, because these are the same.
Yeah.
About stack canaries.
I kind of wonder the same. So let's
okay. Yeah.
Maybe I learned something.
Yeah, there were 2 questions about stack canaries or stack cookies, which was this random value that Marit talked about that's being placed on the stack. And I guess the only reasons for removing them is either if performance is one, there's some performance overhead of doing this, and if your system is very sensitive to performance, I guess it's a valid reason. Another one would be like your weird CPU architecture or compiler doesn't support it, or you're running or writing code for a chip that doesn't have this enabled, because this random value has to come from somewhere, and I guess on Linux and Windows and Mac and so on, it comes from the operating system. So it's like the stack canary is read from a magic register or something. Yeah.
But even sometimes one can bypass stack cookies as well. And we do that often in hacking competition. So that's not like complete security mechanism either.
Yeah. But you usually like need an additional vulnerability, which kind of raises the bar for attackers. And yeah, in 20 seconds we're out of time, so maybe we should.
Yeah, let's just do like. I think you can hide it, and then.
Yep.
All right, you're awesome. Thank you.
Thanks for watching.